In this video, I'm going to begin to discuss the beginning of Chapter 3 on remote sensing systems and specific missions. I'm going to give a broad orientation to kind of what the chapter is about, why is it included in the book, and why are we reading it, and some more details about a few types of resolution and how they relate to what we learned in a prior chapter, prior topic on reflectance behavior of materials. So as I said, the chapter is both about kind of these what I call here general properties of making measurements via remote sensing, general properties and constraints of that process, and the actual ways that they've been implemented. So here, specific missions, if we talk about kind of government efforts, or I don't know, different sensor systems, if you look on the commercial side. Kind of, you need to understand some of the trade-offs that are present, some of the typical properties that describe the data that might limit what can be observed. And it's good to see how those have been worked around or implemented in the past to understand kind of where to go to for certain data types or for data for certain types of applications. And also understanding maybe what interesting things haven't been done, I guess, the gaps, the ways to address that going forward, what might be done. We'll begin with the topics of resolution. And resolution is more or less precision in the measurements that sensors are making. You can also think of them, and sometimes it's discussed like this, as characteristics or properties of the data products that are created through that process of remote sensing. So the first one that's mentioned, and really the kind of, I call it the most basic type. If you hear somebody just talking about resolution of remotely sensed data, they're typically talking about spatial resolution. And as the book talks about, spatial resolution is a function of the instantaneous field of view of a sensor, which is a function of kind of the height, distance between the sensor and the object it's observing. It's essentially the smallest spatial unique observation, or discrete in a separable sense. If you see a data product, spatial resolution is typically described as the length on one end of a pixel in that image. Pixel being picture element or grid cell in that raster data product. So spatial resolution is kind of described here in figure 3.3 in the book. I think figure 3.3 is it's a very good figure, and it kind of is a way that we can connect the lessons in chapter 3 to what we've seen before, namely spectral signatures representative of cover types. So in this example, there's kind of reddish, blue, green, yellow, that are different materials on the ground in such a way, and it's kind of geometrically like planned, laid out fields or something. And then overlaid above that, we have some sort of grid pattern for different pixel sizes or different spatial resolutions. So kind of the big pixel size that's taking up a quarter of this area, kind of the cells that are taking up about a 16th, 4 times 4, or a quarter times a quarter, and then those that are taking up about a 64th. And it's a good example of, the book talks about this, of how when you go from smaller to larger grid cells, you're more likely to have mix of cover types within the area of the grid cell. You might hear somebody say it's the footprint of the grid cell. Now that doesn't have to be the case. We see in the bottom right grid cell, it's all a single cover type, this yellow with a reflectance of 0.8, whereas these tiny 1/64th grid cells can be mixed between two cover types. So it doesn't have to be the case, but just given that cover types are of a certain size, I guess, and they only make sense at certain scales. You know, if you're talking about a forest, forest is a cover type that makes more sense when we're thinking in broader scales. You know, if you're measuring things at a resolution of a meter, very fairly high spatial resolution, you know, you'll have multiple pixels measuring reflectance of a single tree crown. And so talking about what's forest using very high spatial resolution data like that can be a little bit tricky because you're making multiple measurements for individual trees. So in general, there's a mix, a greater chance of mixed pixels at larger spatial resolutions, but it's no guarantee that that's what you're going to encounter. We also see overlain on these cover types numbers in black, and there's kind of one number within each imagined grid cell, and that's reflectance. And I make a note here in the slide that these legend values and the values we do see overlaid here, they represent, say, reflectance, but only for a single band. So earlier we saw the spectral signatures that showed how different materials would reflect light of different wavelengths to different extents. So this would just be, you know, how do they all reflect red light or near infrared light, say. See, there's a range, but that based on the degree to which a grid cell is mixed and the specific components that are kind of part of that mix, you'll have an aggregate or a composite, some sort of a combination measurement that takes into account what is there within the footprint of the grid cell, but also how prevalent is it. So we see for this big grid cell in the bottom right, all of its footprint is within this yellow category, so it has a reflectance of 0.8. For green up here, we'd see 0.5. And so for the upper right grid cell, its reflectance is 0.6. Taking note that most of its footprint is this green category with a lower 0.5 reflectance, but a little bit along the bottom edge is yellow and would have a 0.8. So a lot of the models that we'll use to try to estimate sub-pixel abundance of different categories, just take a linear modeling approach. So it says, well, okay, if there's 3/4 of the cell footprint is green, 1/4 is yellow. Well, if we know the reflectance of yellow and green, we can just weight these values by the fraction. So it would be 0.5 times, say, 0.75 plus 0.8 times 0.25, so long as those proportional coefficients sum to 1 or account for the total footprint. So we'll get into that in a little bit. So just note that for each grid cell, no matter how big or how small, to the extent it's mixed, the spectral signature, or how that pixel, or how much reflectance is observed for that area, will vary depending on the components, specifically kind of what color, and how much of each is present. So it's going to be a mix. This other figure on that relates to spatial resolution of sensors. So the pixel size of their data products on the vertical axis, and here on the horizontal, the year, I guess, in which they came out or they're dominant. What I want to stress in this figure is that, yeah, there is kind of a progression in the later decades of the 20th century toward the availability of higher spatial resolution data. But for things like geostationary data, there's still a need for that, or there's still a use for those kind of data. Um, Geostationary satellites have an orbit that um, positions them over the same location on Earth at all times. So their orbit is in sync with the rotation of the Earth. They essentially will always gather information or take measurements of the same. Now, those that in order to have an orbit that is in sync with the rotation of the Earth, they have to be pretty far away from the surface of the Earth relative to a lot of other satellite sensors. And so the spatial resolution of the data is pretty coarse. It says here about 5 kilometers squared. Now that those data are still very useful, despite having a pretty massive pixel size, because they can take observations very frequently for the same area. And so if you have questions about processes that can change during the course of a single day, such as rainfall amount, say, or photosynthesis, kind of plant behavior, data from, or any kind of flux really, data from geostationary satellites can be very scientifically useful. And so there's still a kind of a need for that. And, this part of the graph is empty, just as another thing I'd emphasize. This part of the graph is empty, but there was definitely a demand for high resolution remote sensing data back then. It was all just spy planes, really, high altitude U-2 planes. Um, they just weren't, the technology wasn't at a place where they were, that the kind of information needs of, say, government actors were being filled by satellite platforms. And well, I mean, in all these decades, there were uh, certainly into the 70s and 80s, but kind of the earliest satellites were not designed to take images at this resolution. And then finally, I'll talk about this figure 3.4. Kind of, we see it has different parts. Have an idealized reflectance curve, a spectral signature in the visible wavelengths for green vegetation and senescent vegetation. So that's kind of like autumn time, kind of the maturing leaf canopy here. And that's the kind of bluish gray profile. So green vegetation, higher green reflectance, lower in the blue and red ranges of the visible. So the figure means to show how useful satellites with increased spectral resolution can be. So spectral resolution here, talking about the different and the different wavelength ranges over which reflectance are observed, and I guess the specific location and width of those. So how precisely are they looking at light of only 0.421 micrometers, or over, say, a range from 0.4 to 0.47, I guess. So the kind of bottom left panel here means to show that if only one observation was made of all the reflectance across those 0.3 micrometers, or 300 nanometers, you might say, of the visible range, these two materials would actually have fairly similar average reflectance, and so would be hard to discriminate or tell apart from one another. On the other hand, we see those three visible bands in a lot of sensors that have gone up. And using, if we have a discrete or distinct blue, green, and red band, the green vegetation and senescent vegetation are pretty easy to tell apart. Green would typically have higher green reflectance, senescent higher in red and blue. And so you can come up with certain kind of threshold equations. So if you look at that, that's a 20% reflectance. You can say, well, if this line would be 17%. So if your pixel has 17 or higher percent reflectance in the green band, it's likely green vegetation and not senescent. If it has lower than 17% reflectance, we could call it senescent. And you don't have to base that distinction on just green reflectance. You can also look to red or blue. So I think the figure does a good job of what Chuvieco wants to do, but I think it actually has a few other kind of valuable lessons for us. The one is in showing radiometric resolution. So if we think of spectral resolution in this spectral signature space as talking about precision or the kind of the level of detail along the horizontal axis. Do we have just one band or three? Radiometric resolution is essentially precision over the vertical axis. So if we want to set a threshold at 18% or 17%, can we reliably distinguish 17% from 18% from 19 to 20? Can we distinguish reflectance to the 10th degree, 20.1 to 20.0? That's the radiometric resolution. And so if you have really poor radiometric resolution, you might not be able to distinguish these two or even these. Whereas if you have very high radiometric resolution, you might be able to. There's a greater chance that you could. But I'll note also that within these classes or categories of green vegetation, senescent vegetation, reflectance behavior is going to differ a little bit. We talked about some of the reasons for that. Could be the direction of the leaves, could be the angle of the sun in a given day. Could be, I don't know, whether or not the wind was blowing when the image was taken. There will be within class variation. So some pixels having slightly more, some slightly less reflectance than others. And that's going to be real variation that needs to be accounted for somehow. And so radiometric resolution, you can increase it means a greater degree of being able to distinguish difference, but those differences can be real, but might not be ones that you want to actually incorporate in your analysis. So just kind of think of that. That's a back of the head kind of thought. But this figure, kind of through horizontal axis, referring to spectral resolution, you can think about the vertical axis, precision across that relating to radiometric resolution. Does a good job of showcasing those properties.